Oh, looks like we're there. Welcome back, folks. So we're about to finish off our Chapter 9 on differential equations, at least the topics that we intend to cover. But before we start today, any questions folks would like to discuss? Should we head right in? Just dive right in? Okay, let's start. So we defined what was meant to be a first-order linear differential equation. It has to be an equation which algebraically, some way, somehow, you can express in that particular format, where p of x, q of x are continuous functions. Then we discussed, in some problems, you may not necessarily need the following step. But for solving problems that are in this particular form, we have the following strategy. We multiply both sides of the differential equation by the so-called integrating factor. That integrating factor is defined to be a new function which we indicate with the I to stand for integrating factor, which depends on the dependent variable x, or in applications very common t or something else, and it's the exponential raised to the power of the antiderivative of the first function p of x with respect to x. So if we multiply both sides of that differential equation by that particular quantity, where we take the simplest antiderivative, then we can solve the equation. And by taking the simplest antiderivative, what we mean by that is you don't have to include an arbitrary constant in integration when we're defining the integrating factor. We would take that constant to be 0 just to simplify the algebra, since any one of those integrating factors would work. Any questions so far about that strategy? Okay, let's try a problem then. So a typical problem that would require this looks about like this. The instructions say to solve the initial value problem, which will abbreviate to IVP once we've written that out a couple dozen times. The initial value problem is cosine of x times y prime plus sine of x times y equals 2 cosine cubed x times sine of x minus 1, where we want the initial value of the solution curve to satisfy y at pi over 4 equals to 3 times the root of 2. And we also have a domain issue since we're dealing with trig functions. The domain restriction on our solution curve is that the independent variable x is constrained to be larger than 0 or equal to, but not exceed pi over 2. So that's the entire differential equation we'd like to solve. But the integrating factor will solve this. First things first, though, we should do a quick check. As the homework problems indicate, it's important to see if you actually need an integrating factor. And this is what that check would look like. If we take the function here, cosine x, d dx of cosine x is negative sine x. So now if we look at our function, if there was a negative sine x right here, then the problem would be almost over. We'd be able to undo the product rule for differentiation and immediately start to get the solution to this. So having a plus sign has completely changed the field or changed the situation. It means we really do require an integrating factor. Since this is not equal to positive sine x, we require I of x. So we'll evaluate what I of x is in this problem, multiply both sides of the equation, and go from there. But any questions first? Okay, one other problem with this is I of x is not e to the power of sine x. Before you go to write the integrating factor I of x, you must have a coefficient of 1 here. So our first step is now going to be divide all sides of this equation by cosine x. If we do that, we're now down to y prime plus sine x divided by cosine x times y equals, divide it here, we'll have 2 cosine squared x sine x minus 1 over cosine of x. So now that's our equation to solve. Then it's really a trig problem in some sense when we're looking at this one. So I think that take this as a great opportunity to review a whole bunch of facts about trig. First off is, what would be this as a trig function? Sine divided by cosine. Yeah, so we now have the equation y prime plus tangent of y equals, well, this, let's just copy as 2 cosine squared x times sine x. Well, we can simplify 1 over cosine x, just in case it's required. So we'll call this a secant x. So we've converted that equation to this format here. That's important because the integrating factor, I of x, is defined in terms of the equation being written in that form. So once we get to this stage where y prime has a coefficient of 1, I of x then becomes e to the power of the antiderivative of that function, hang on, that should have been a tangent x with a variable y. That was miscopied, it was thrown into the wrong place. So e to the power of the antiderivative of sine x over cosine x, which was tangent x dx. So that's our integrating factor so far. Any questions to that step, folks?
Is the cosine supposed to be cubed, right? Or...
Oh, it reduced by 1 power once we divide cosine
yeah,
into all the terms. Yeah. Other questions about it? Okay, so if this was an exam problem, finding the antiderivative of tangent x, it's a doable problem. But notice that is a whole lot of extra work, and that's a problem that we've solved several times before. So whether you're doing homework or taking an exam 2 next week on Thursday, you should look at the notes provided on exam 2. It's pretty similar to the notes provided on exam 1, except that once you go beyond the table of common derivatives, there'd be a table of antiderivatives. These are results that you can take for granted if you like. Whether in an exam situation or working at homework, if you just tell me right away that the antiderivative of tangent is the natural log of secant in absolute value plus a constant, then that'd be acceptable. So we can come over here and say I of x is e to the power of the natural log of the absolute value of tangent x. We won't throw in a constant of integration because we're taking the simplest antiderivative possible, which would be that one. So we're on our way. Any questions first to this step? Another common feature people are going to see in their homework is that somehow, some way, these absolute values are going to be able to come off. And this domain is what's making that happen. On the domain from 0 to pi over 2, tangent itself would be positive. Since the graph of tangent looks about like, oh, I missed really bad on that one, looks about like this, where this is pi over 2 with a vertical asymptote. So the absolute value bar would come off on this problem to get e to the power of the natural log of ordinary tangent x. But then base e exponential and the natural log are inverse functions, so we immediately have the cancellation that the integrating factor is tangent x itself. So we've done several things so far. We found that the derivative of cosine is not positive sine, so we had to divide everything by cosine. We found the integrating factor, and now we're about to multiply both sides by tangent x to solve the equation. Any questions before we get to that step?
Shouldn't it be e to the ln of secant?
Oh, it should be. Thank you. Miscopied that as a tangent. Should have been secant. Thanks for spotting that. Secant x here, here, and here. That's one of those unfortunate errors that carries down several steps. At least we spotted it right now. Thanks for mentioning that. Other questions to that step? So take secant x, multiply it on both sides of the equation, and we would have that secant x y prime plus secant x of tangent x times y would be equal to, when we multiply by secant x, we're in fact multiplying by 1 over cosine x. So there's a cancellation here, and the power drops by 1 more. Now we're down to 2 cosine x, sine x. We multiply by secant x over here, and we get negative secant squared of x. So it's looks like it's getting better. It looks a little bit worse, but sometimes these things get worse before they get better. Any questions, however, to this step? Okay, then there is a built-in check right at this step. Before we undo the product rule, notice that in the very first step, we were looking for this condition, where if the derivative of cosine was negative sine, we would not have needed the integrating factor. So we look over here. If we look at d dx of secant x, that would be itself times tangent x. And that check tells us we have just the right quantity here so that we wouldn't need the integrating factor. It's kind of a nice tune. I like that.
So sorry.
You're fine. It happens. It happened to me yesterday, actually. Questions at the moment to that step? Yeah.
Can we go further? So say this doesn't work out, like those two didn't match.
Yeah, right here, you mean?
Yeah.
Well, it would meant that something has gone wrong, like I put a tangent there. It would imply a mistake right at here.
But we couldn't try again, like put it into that form again, and
Well, we possibly could solve something, but we would no longer be solving the original equation, would be the problem, yeah.
okay, good.
Yeah, so getting a tangent there at that step was problematic. Would mean I do not have what I need. We need to figure out what went wrong.
Gotcha.
Other questions to that step? Okay, so since we have the derivative of secant by y prime is the coefficient of y, we can undo the product rule. And we mentioned that this is an optional step, but it's also the logical glue of why all of this works. So let's write that step, which says d dx of secant x times y, with the multiplication there to emphasize our check here would be really a product rule. d dx of secant x times y would be, say, take the derivative of y first. You would have to copy secant x, y prime. Then the product rule says add. Now I'm going to take the derivative of secant. But the derivative of secant is itself times tangent. And we copy the opposite function, which would be y. So from here to here, we have, through this check, indeed undone the product rule. The right-hand side is really just a huge mess, but we can do something helpful here in finding the antiderivative. The 2 cosine x sine x is a double angle identity, which gives us 2, or rather sine of 2x. That just simplifies the process of finding this as an antiderivative, minus secant squared of x. So from here to here, we have undone the product rule. Again, this is a skippable step, but it's showing the logic of how this is working. The next thing we're going to do immediately is take the antiderivative of both sides with respect to x. So the equation would convert to this statement so far. Any questions then to that step? So this is the major trick of why the integrating factor solves the equation, because if we can undo the product rule, which is what the integrating factor allows, then we have a statement that says the derivative of secant x form its antiderivative, but that would just be a straight cancellation. And it would give us secant xy equal to antiderivative of sine 2x. Well, the antiderivative would be a negative cosine of 2x. Since the derivative of negative cosine gives us the positive sign, by chain rule, we need a half there. Then we go minus antiderivative of secant squared. But the derivative of tangent is secant squared, so this would be minus tangent squared of x. And we throw in the constant of integration. So that would be our steps so far. Any questions to that step? Okay, and all of these type of problems, as soon as you get to this stage, we can always solve for y explicitly. Because we have the integrating factor secant x, we just divide both sides by it. But notice, if you multiply by cosine x, then cosine times secant would be a cancellation, since secant is 1 over cosine. So I'm going to solve for y just by multiplying both sides by cosine x. So that's what the algebra would look like so far. Cosine cancels with secant, and we get y is equal to negative 1/2 cosine of 2x times cosine of x. Then we take negative tangent squared x, or excuse me, that should have been tangent x itself. Derivative of tangent x was the secant squared. That should have been a power of 1. So tangent is sine over cosine. So if we multiply by cosine into tangent, we would just get an ordinary sine x plus cosine x times that constant c. That's a lot of algebra in one problem, but any questions to that step? So we've essentially found the general solution to the ordinary second order differential equation here, but now we want to solve the initial value problem. The initial value was that y at pi over 4 needs to evaluate to square root or 3 times the square root of 2. So we'll do that as our very next step. After we clear off some space to work with, let's do it, say, over here. So we're told that y at pi over 4 should evaluate to square root or 3 times the square root of 2. But we now know the function y itself. So we can take y, evaluate this at pi over 4 would be inserting pi over 4 into all places that contain x. So we would get negative 1/2 cosine of pi over 4 times 2, that would be pi over 2. So we're inputting pi over 4 into all places x. Then here we have cosine pi over 4. Then minus sine pi over 4. Plus cosine pi over 4 times the constant of integration c equals 3 root 2. So the left-hand side is the evaluation. The right-hand side was the output of the initial value problem. Any questions to that step? Okay, this looks really bad, but one thing to look at is what would be the evaluation cosine pi over 2? Yeah, that evaluates to 0, which is fantastic, right? It's reduced a whole bunch of work. All of this is gone. Sine at pi over 4 would be root 2 over 2, so we get negative root 2 over 2 plus cosine pi over 4 is root 2 over 2 times the constant c, which is equal to 3 root 2. Any questions to that step so far? So we can solve for the constant c by first adding 2 root 2 to both sides. So we're back to ordinary wonderful algebra, solving for a constant. We'd have 3 root 2 plus root 2 over 2. Then we can multiply both sides by the reciprocal of root 2 over 2. So I write that this becomes 2 times, or 2 divided by root 2, multiplying the left-hand side, 2 over root 2 multiplying the right-hand side, gives us the constant c equals, this multiplying this would cause the root 2 to cancel, giving just a 6. We multiply this way to this way, the 2's divide, the root 2's divide, and we just get a 1. So the constant of integration is exactly 1 itself. Any questions so far? Or excuse me, 7. I'm going to blame the cold on that one. So the constant of integration is 7. So we can go back to the problem here. And if you did this in your homework or an exam, I would say it's forgivable. You need a new line that says y is all that stuff with a 7 for c. But if you kind of did this, I'd be perfectly okay with that. Is that okay with everyone if we do that today? Okay, it's hidden a step, but that is a quality of life improving shortcut, I would say. But any questions so far with that process of solving the differential equation? Okay, this one was meant to be kind of a longer one, where we focused on the shortcuts you can take, the things to watch out for if you can possibly skip a step. But that's the main type of problems that we're going to be looking at this section. And if folks like, just for the fun of it, we could go and solve an application. This application would be for circuits. Does that sound fun to folks? Circuits? I have 1 yes, 1 no.
Yes.
Some yays? Sorry, we'll give you a veto on the next one. Does that sound all right, Kylie?
No, that's fine.
Okay, so let's solve this problem with the circuits. So I've never taken a circuits class, but that's okay. That's nice thing about calculus is if you know the meaning of each symbol, you can still at least solve the differential equation. So they tell us here we have a circuit diagram. The figure below shows a circuit containing electromotive force, capacitor with a capacitance of C farads, no idea what those units are, and a resistor of resistance R ohms. The voltage drop across the capacitor is Q divided by C, where Q is charged in coulombs. And here's a major theorem. Kirchhoff's law gives this statement here, where I is defined to be current. They say see example 3 in section 3.7, where other terms are defined. But the definition of current in that example is dq dt. So this is where we're going to start. This is our differential equation that we would like to solve. So let's copy that first. Our equation takes the form of r. dq dt is helpful because Leibniz notation tells us what the independent and dependent variables are. But if you wrote this as q prime, that would be just fine as well, if we're clear on the meaning of the variables, plus 1 over capacitance times q is equal to E of t. So that's our setup so far. Any questions to that step? Okay, the next tell us, we're not trying to solve this in full generality. We're looking at a specific situation. We're told, suppose the resistance is 5 ohms. That is ohms, yes, and resistance was R. So we have 5 here times Q prime plus, next they say the capacitance is 0.05 farads, where that came from C. So we have 0.05 in place of C, so 1 over 0.05, or 20 if you prefer, times Q is equal to, and they say a battery gives a constant voltage of 60 volts. That's what they mean by E of t. The problem doesn't define it. They want you to go back to example 3, section 3.7. But that's the meaning of E of t. So E of t is the voltage, and they tell us we have 60 volts on the right-hand side. I'll drop the units in and just write 60. So that's the setup so far. Finally, they say the initial charge is Q at 0 is equal to 0, which seems about right. The charge, we shouldn't start with a system that already has a live charge on it. That sounds really dangerous. So that's our setup so far. They tell us find the charge, which is Q, and the current at time t, where I itself is that current. So first thing to do is we need to solve this differential equation. Any questions so far with the setup? Okay, so if you build something like this, you can now say exactly what the charge has to be with this configuration. First, let me just simplify to say that we're dealing with 5q prime plus 20 times q is equal to 60. Then we do a check on this equation. The derivative of 5 is 0, so we do need an integrating factor. Before we get an integrating factor, we have to first make this a coefficient of 1 by q prime. So we're really just copying the same steps as before. In fact, this is a nicer problem, I would say, than the very last one. Really, the awful thing about it is you have to say what the meaning is for R, C, Q, E of t, and I all at the same time. So there's lots of vocabulary floating around. But if we divide by 5, we get that q prime plus 4q is 12. And we're ready for our integrating factor. That integrating factor is, once again, I of x. Which is defined to be the exponential to the power of whatever is here as a function, including the sign. So if I have negative, we would have to carry that negative. But here it would be a 4 dt, since the independent variable is t for time. So that integrating factor evaluates to e to the power of 4t. Does that look all right to folks, to this step? Okay, once we have e to the power of 4t, question becomes, what do we do with it actually? What happens to e to the power of 4t in the differential equation?
Are we meant to multiply both sides by it?
Exactly, yeah. So we just take this quantity, multiply the left and right hand side, and we get e to the power of 4t, q prime, plus 4 e to the power of 4t times q is 12 e to the power of 4t. So we made the equation much, much worse, but it's just how it goes. And I would always do this check just to see if I'm on the right track. We want to look at d dt of e to the 4t, which is the coefficient of q prime. That works out to e to the 4t multiplied by the derivative of 4t, which is 4. But this entire quantity is now the coefficient of q, which means that integrating factor was done correctly. And we can immediately skip to a shortcut if we like. the punchline is e to the 4t q is the antiderivative of 12 e to the 4t dt. In the previous problem, we showed the step that's missing that gets us to that stage. But does that make sense to skip down to that portion? Okay, so if you're happy with that, then the next thing to do is actually find the antiderivative. So we'll have e to the power 4t times q equals e to the power 4t antiderivative is e to the power of 4t itself. We would have to divide by 4 to take into account the chain rule, and that would divide the 12. So we get 3 e to the power 4t. Then just visualize if you were to differentiate this, you get e to the power 4t, 4 comes down multiplying the 3, producing the 12. So that's what we're expecting, and now we need a constant of integration c. Any questions then to that step? Okay, then q, which was, what was q? Charge? Let's go back here. Q is charge. Charge is solved for as soon as we divide by e to the 4t, or if you prefer, you can multiply both sides by e to the power of negative 4t. If you went that route, and both routes are perfectly fine, e to the power of negative 4t cancels this quantity, and multiplies the constant. So it could be written in that form. So now we found the charge at any time t. But we want to find the specific charge. This is a whole family of solution curves that satisfies the safety condition by OSHA that at time 0 we should have charge 0. So let's do that portion next. Any questions to that stage? Okay, so let's say if q of 0 is equal to 0, and this is our q of t, or you could leave it as q if you prefer, then chalk is very brittle this day. We would have 0 is equal to, input 0 into this function would give us 3 plus e to the power of 0, which is a 1, times c. So the initial condition is solved up for as soon as we subtract 3, and c is negative 3. C might have been a bad choice because recall C has a different meaning up there. So if that bugs you, it kind of is bugging me, you can give it a little extra decoration. C sub 1. So now it doesn't conflict with the different meaning of capacitance. So now we have that Q at any time t, which is charge, is 3 plus, or rather minus 3 e to the negative 4t. So we satisfied half the problem, which said find the charge at any time t. Any questions then to that stage? So if you build this to that specification, that would be your charge. And as time proceeds, it looks like the charge is going to converge to exactly 3, because in the limit, this quantity is going to get smaller and smaller and smaller. But the next thing it asks us to find is, let's identify that as charge. We also want current. So the current at any time t would be I, which is unfortunate because that's different from the integrating factor, so we have to keep those symbols separate as well. Let's just call it I. Oh, this should have been I of t rather, to match this independent variable. I is defined to be the rate of change of charge at any time t. So as soon as we found charge, it's just one quick step to get current itself. So we take the derivative of this quantity, it produces 0 here, then it'd be negative 3, derivative of the exponential is itself, multiplied by negative 4 with the chain rule, so we have that the current at any time t is equal to positive 12 e to the negative 4t. That tells us as time proceeds, the current is tending towards a current of 0, which seems about right. Not that I'm an expert at these kind of diagrams. Any questions so far with that kind of problem? So that's a neat way that first order differential equations enters into the sciences. And there's many other different kinds of models. Some of the things we didn't look at are various population growth models, exponential decay models, and so on. But that's a typical example of first order linear differential equations. It's a mouthful. Any questions so far about the subject? That really completes all of Chapter 9 that we intend to cover. It's mainly meant to be an overview of more applications of integration. The next thing we're going to do is move over to Chapter 11, where this is essentially the goal we're working towards in this new chapter. So chapter 11 is titled Sequences and Series. It's quite a large chapter. It's, I think, the largest chapter in the entire book with 11 different sections. And this is the goal. We want to find an alternate way of finding antiderivatives to functions such as, say, e to the x squared. We have lots of problems with functions like that. In fact, many functions, such as sine x divided by x and such, have no elementary antiderivative. We can use the fundamental theorem of calculus, part 1, chalk is going everywhere, which says the antiderivative of e to the x squared dx can be written as the definite integral from 0 to x, e to the t squared dt. If we want the most general antiderivative, we'll throw in a constant of integration c. But that is in some ways a cop-out. Sometimes it's the best we can do. But if we can find a better approach than this without invoking that fundamental theorem of calculus, then it'd be something useful to have. There's also other great things in chapter 11, but this is one of our major goals, to sidestep this kind of process and find a better formulation for e to the x squared. We'll find over the course of doing that we need to say what e to the x actually is. It's considered a transcendental function, which is in the cover of your book. It's single variable calculus and transcendental functions. It's transcendental in the sense that if you want to write a formula for this, you're forced to do something along these lines. The summation as I goes from 1 to infinity of x to the power of n divided by n factorial. In other words, we can redefine e to the x in terms of a series involving infinitely many terms. To get to that point, we have to first start with sequences, and that's our section 11.1. Any questions so far with that? Okay, so that's what we're trying to go after. If we can use this formula here, we can find a better way to get an antiderivative. It's still not great. There will never be a closed form solution to the antiderivative of this, but it's sometimes better than this approach in the right context. So to get to that point, we're going to start all the way in section 11.1 on sequences. Let's call this section 11.1, sequences. So the first thing we need to do is we need to say exactly what we mean by sequences. All of our sequences are going to be an ordered list of terms. That list has to be infinite in this context. And so we can say for a definition, a sequence is an ordered list, A1, A2, A3. If we like, we can emphasize that this list goes on forever by saying we'll list a whole bunch of terms until we get to the nth term, but then continue well beyond it. So we're going to have infinitely many terms where A sub n is some real number. So in other words, sequences are really a special kind of function, where if I input 1 into that function, I would get a1, which is some real number. Input 2, I get some other real number, and so on. Here, the sequences are going to be real numbers because that's the nature of our course, single variable calculus of a real variable. But in other classes, that could be a complex number itself. So that's what a sequence looks like. Any questions about it? Another common feature in chapter 11 that we see in a lot of sections in calculus is notation is sometimes something to get used to because there are many, many notations for the same thing. So if I have a sequence that looks like this, we can repackage that into the various notations. These notations are important to keep in mind because various formulas involving sequences and series use these different notations all over the place. So let's write the following. this sequence can be denoted by sometimes we just use a set. And we throw all the terms into the set and write the set that contains A1, A2, A3, and so on. We'd only put up to AN if we really want to emphasize it's an infinite sequence. So that's one common notation for a sequence that we'll see. Another way to write this is we could say it's the set AN as n goes from 1 to infinity. So that's something you'll see in formulas quite a lot as well. And another notation you'll see in formulas is the following. Sometimes this is just really tedious, and we, to simplify things, just call it AN. So that would be another way to indicate the sequence. Or another way, another option, is to define the sequence by A sub n equals some formula. So sometimes we don't bother by writing out these brackets with set notation. Sometimes we just say, give some formula for the nth term, and that'd be a fine way to define the sequence. Seems to be common for lots of problems in the homework, but this would be, or this option, more common whenever you're dealing with formulas involving sequences and series. But probably the next thing we ought to do after looking at the definition, common notations, is let's just look at a sequence and see what we're getting into. Any questions first with the definition? Okay, so let's look at an example of an actual sequence. This says to consider the sequence. I'm going to go with this notation. The sequence is going to be defined by A sub n. I need to write some function of the nth term. And that function could be really your imagination. Could get pretty wild with these. Let's go with a cosine n pi and divide by 2 to the power of n. So that'd be a typical way to express that. Or you could say it's cosine of n pi divided by 2 to the power of n as n goes from 1 to infinity. In some ways, this is a better notation because it tells us the starting term is 1. Starting term could very well be negative 12 or 0 and so on. So that gives a little bit more information. But this is quite common. So let's say for the first portion here, plot the first 5 terms of this sequence. Let's call this a part A. So that's a decent exercise to do. The homework is also going to ask you to do this. And when you do this problem in chapter 11.1, let's see here. Problem 20 is about what we're about to do, and it's quite a large problem, which comes into 3 parts. So that one will be worth 15 points. If we want to plot the first 5 terms, really we're just trying to find the values of A1, A2, A3, A4, and A5. Then we'll plot those values on an XY axis. Any questions before we start? To do that, we're really just using the function notation. So A sub n, really we could have just stuck with f of n when we define the sequences, but you save about 12 cents on printing your textbook if you do A sub n. It's slightly easier on the typesetting. So we go over here. A sub 1 is inputting 1 into the function, so we would get cosine pi divided by 2. So this is cosine of pi divided by 2. At A sub 2, it'd be cosine of, throw 2 into the value of n, so 2 pi, divided by 2 to the power of 2. A sub 3 is cosine 3 pi divided by 2 to the power of 3, and then so on down the line. Let's just write these all out. Cosine 4 pi divided by 2 to the power of 4, and finally cosine of 5 pi divided by 2 to the power of 5. So that's the evaluation of all of these. We're going to plot them, so we also need to evaluate the trig functions while we're at it. So what would cosine at pi be? Yeah, here we would have our -1 here divided by 2. So -1/2 on the first one. Then we just go down the line. Cosine of 2 pi is the same as cosine of 2, which is +1, divided by 2 squared, which is 4. Cosine of 3 pi is the same as cosine of pi. Through periodicity, we're just repeating the values. So it's -1 in the numerator divided by 8. Then at 4 pi, we would get +1 divided by 16. At an odd pi, we're getting -1, and this would be divided by 32. So in the evaluation of cosine, even values produce a positive, and negative values, or odd values, produce a negative. So we're ready to plot. Any questions first before we go to the plot? Okay, so the plot would look like this. Here we have n, we're going to plot as the horizontal axis. In the vertical axis, we're plotting a sub n, all of the evaluations. And we're definitely going to use a different scale for the horizontal and vertical axis. That could be convenient. And we notice that the largest value is at -1/2. So I'd go with a -1/2 here to set the scale. So about here looks like it'd be +1/2. Then we're inputting a 1 as the first value into the function, so I would sketch with a 1 here. You don't have to necessarily count these off, but I'll start with a 1 here to indicate the scale. So at a sub 1, we have a value of -1/2, and that would be the very first term of the sequence so far. Then at a sub 2, we had a value of 1/4, so that would be half the distance here, giving us this value in the sequence. So this is kind of a handy thing to do because we have a sequence. A lot of the questions we want to ask are, does the sequence converge or diverge? Much like what we've done with improper integrals. Being able to visualize what the sequence actually looks like on a, say, a sub n axis helps us to determine if it may be convergent or divergent. So at 3, we get -1/8, so this is a fourth, meaning this is an eighth, and we get this value. At 4, we get a 16th, so this is getting harder to plot. So that was an eighth. This is a 16th, and we're here. That's 4, that looks about right. So at 5, we have a 32nd. So that was an eighth. 16th, a 32nd is, these tick marks are now getting a little too large, about here. There's infinitely many more terms, but that's what the first 5 terms would look like. Any questions then so far? Okay, let's add a part B then. Part B would ask the question based on the plot of a sub n, which is defined as cosine n pi divided by 2 to the n, does the sequence converge or diverge? Maybe it's an unfair question at the moment. We haven't defined convergence, divergence just yet, but we're about to, and the intuition will be based upon what we see on this graph here. So what would you say this picture looks like? Does this look like a convergent or a divergent situation?
Conversion.
Sorry, what was that?
Conversion.
Yeah, this would be convergent. So we can say the sequence converges. First, why would you say it's definitely a convergent picture? What feature of the graph says convergence, definitely?
Because it's progressively getting to 0.
Yeah, the values are tending towards a specific height. That specific height is to 0. So if all the point values, heights, are getting closer and closer to a specific value, that's what convergence would look like. If the points are not getting closer and closer to one specific number, we would say it's divergent. But any questions so far about that?
So that number it converges to doesn't necessarily have to be 0.
It does not. It could be any real number whatsoever, correct. What it cannot be is infinity or negative infinity. Those cases we would say it's diverging, either towards positive infinity or diverging towards negative infinity. But the number we're converging to in this case was 0, and it can be anything else. Other questions about this so far? Okay, let's define exactly what we mean by convergence and divergence next. Then we're going to do some problems where we look at ways of deciding, without having to use a graph each and every time, whether certain sequences will converge or whether they'll diverge. But first, this will be our working definition for convergence and divergence. So we start as follows. We let A sub n be a sequence. So this is the laziest of notations you could possibly use. If you want to be more specific, you could say it goes from 1 to infinity, but that would be in the context of the entirety of chapter 11. They're always an infinite sequence. We then say, then A sub n converges to a real number. Let's denote it by n to say it's a limit, since this is really a limiting process. It converges to a real number, L, if the terms of the sequence gets closer and closer to L as n, the index itself, gets larger and larger. Well, we did say we want to give the exact meaning of convergence. This is not quite it. If we want to give that exact meaning, we'd have to give an epsilon delta definition. But that was an optional section in Calculus 1, so it's typically skipped in this section, and it comes back if you're ever going to take elementary mathematical analysis, Math 3326, or something along those lines. But this would be a good qualitative definition of what we mean by convergence. We can say then, in this case, what I mean by in this case, the sequence converges to L, we write the limit as the index n tends towards infinity of A sub n is equal to L. And there's a specific epsilon definition we could give to that particular equation. But any questions so far about that definition? Okay, then the second part of the definition says, if A sub n does not converge to any real number L, then we say A sub n diverges. So that's kind of a cop-out of a definition. It says if a sequence does not converge, that means it diverges. But that means there's no specific value L for which this limit holds. So there's no number L such that n will get closer and closer to it as the index n gets larger and larger. So those will be our working definitions for the entirety of chapter 11 for convergence and divergence of sequences. The thing that gets really tricky about this is, as soon as we go to 11.2, we'll be talking about series, where the notion of convergence divergence is a little bit different. So that's something to always be aware of. Any questions so far, however? Okay, I guess I have a question for folks. Just for the sake of completion, we can give the precise epsilon delta definition of this limit. Does that sound like something folks would like to look at? We can leave it up to Kylie. You have a veto power.
Sure.
Okay, let's give the epsilon delta definition of this limit. It's important to know that there is a precise mathematical definition to it, and knowing that precise mathematical definition will allow us to prove many different results that the book does. So this is what we will mean by the precise definition of the limit as n goes to infinity of A sub n equals L. This means for every epsilon bigger than 0, we typically think of epsilons as being very, very small, but they're always positive and never negative. There exists, typically we'd write a delta, but that would be an ordinary calculus. if we're dealing with this situation with the sequence, we're going to use a capital N in place of where delta would have been. So there exists a positive N such that if the index N is sufficiently large, bigger than that large number N, then we'll be within an epsilon distance of the limiting value L. So if N exceeds capital N, then the distance from A sub N to L, written this way in absolute value, will be less than that very small value epsilon that we specified. But this has to work for every epsilon. There exists a particular N, and N is a function of epsilon itself. So that would be the notion of what it really means to have a limit here. It's kind of a better definition in the sense that we said exactly what we meant by gets closer and closer to L. It means you are picking a very small epsilon. We've also said what it means if N gets larger and larger. It has to exceed some large constant uppercase N. But any questions then about that definition? Okay, so the very next thing we ought to do is we should have really good practice on actually computing these types of limits because it's going to become very relevant in section 11.2. So if we're given a sequence, say cosine n pi divided by 2 to the power of n, we should be able to determine if it converges to a value 0 or if it diverges simply by using limit laws. So let's do that very next. Any questions at all first? Okay, this is a pretty fun portion of chapter 11 because essentially what we're doing is going back to chapter 2 of Calculus 1 and revisiting all of those limit laws. And the theorem that's going to tie everything together is theorem number 3 in section 11.1. So let's look at the content of that theorem and what it implies so far. So theorem 3 says the following. If the limit as n goes, or excuse me, x goes to infinity of f of x equals L, this is now an ordinary limit in calculus 2. So if that limit is equal to L and a sub n is equal to f of n, then the limit as n goes to infinity of a sub n is also L. So if I take any sequence a sub n, look at that function, I can convert it into a continuous function. Notice that a sub n is very, very discontinuous. It's just a sequence of dots. But if I convert to a function f of x that's continuous in the variable x, I can resolve the limit here and carry over and assert that would be the same limit down over here. So that's a really, really important theorem because now it tells us every single limit law, oh, I don't think I have that file there, but every single limit law from chapter 2 of the textbook can be applied to finding these limits of these sequences. That's really exciting. Let's do that next. For the problem that says determine if the sequences converge or diverge. Now let's start off with one that goes about like this. A sub n is going to be equal to n times e to the power of n divided by n squared plus 1. So that's our sequence so far. And there are different approaches. You could, for example, build a table involving maybe the first 10 terms of the sequence, plot all those terms, and see if we're tending towards a limiting value. That approach can be dangerous because sometimes our eyes can be deceiving. So we do need a different method. We're going to apply theorem 3. And we'll also mention shortcuts as we look at different problems. So the first step is we'll let f of x be equal to the continuous version of this sequence. So it's just x e to the x divided by x squared plus 1. On one hand, it looks like all I've done is change the variable from n to x. But now x can be any real number. X is going to be positive in this problem because we're taking the limit for large values. Whereas over here, n is going to be just the discrete values 1, 2, 3, and so on. So the positive counting numbers. So that's our f of x. Now what I'm going to do is invoke theorem 3. Let's take the limit of f of x as x tends towards infinity and see what happens. If we get a positive or negative infinity here, that would mean the sequence diverges to either positive or negative infinity. If I get a real number, then I can say by this theorem, the limiting value of the sequence would be that number, so it converges to that number. So let's write that out next. But any questions first before we start? Okay, so we need to take the limit as x tends towards positive infinity of x e to the x divided by x squared plus 1. This can be a terrible limit. Some of our limits have really great shortcuts, but this particular limit we can visualize by saying the numerator itself is going to grow without bound. So we have something that tends towards infinity in the numerator. The denominator is also a quadratic polynomial, and as x tends towards infinity, it also tends towards infinity in the bottom. So this is a type infinity over infinity indeterminate form. But that's just great because that's the specific type of indeterminate form L'Hopital's rule can handle. So we're going to resolve this limit of f of x by L'Hopital's. L'Hopital's rule says if you take the derivative of the numerator, divide by the derivative of the denominator, the limiting value will be exactly the same. So let's do that right away. In the numerator, we'll take the product rule first. The derivative of x is 1, so we'll get e to the x plus, copy x. The derivative of e to the x is itself, and that's our full numerator. In the denominator, the derivative of x squared plus 1 would just be 2x. So that's our new situation. What folks want to do at the very next step then? Would you say it's still indeterminate at this stage? Yeah, it's still indeterminate of the same flavor. It's still of type infinity over infinity. And that's okay, that just means we'll use L'Hopital's rule again, as many times as we need to. So another application of L'Hopital's rule gives us the limit as x tends towards infinity. The derivative of 2x resolves to 2. So this would be the final time we need L'Hopital's rule, because we are losing that portion of the indeterminate form already. The derivative of e to the x above is itself. Then the derivative of x e to the x, notice we've already done that. Derivative of x e to the x was this entire quantity. So it's plus e to the x plus x e to the x. Does that make sense on that derivative so far? Okay, then it simplifies. You could factor if you'd like to. However, as x tends towards infinity, 3 exponential functions, 1 multiplied by x itself, this is heading towards infinity really, really fast. Would you folks agree? So we can say the whole thing is infinity. It doesn't mean the limit exists. In fact, the limit failed to exist, but in a particular way. The values of this function, f of x, get larger and larger as x tends towards infinity. But that means by theorem 3 that a sub n, which is equal to n e to the n squared plus 1, would you say it converges or diverges then by the work over here for f of x?
Diverges.
Yeah, so the whole thing diverges. And it diverged specifically to infinity. We didn't approach any one value at all. There's no real number that the terms are getting closer and closer to. They're just getting larger and larger without bound. So that's the magic of theorem 3. It also allowed us to use L'Hopital's rule while we're at it to solve the problem. Any questions about that problem so far? Okay, I think we have a time for maybe a couple quick limits, then we'll call it a day. When we come back on Thursday, we'll finish off 11.1, looking at other interesting topics, and we'll start 11.2. Then when we come back next week, 11.2 will be finished off. We're definitely not getting to 11.3. We'll review for the second exam on Wednesday and take our second exam on Thursday. So that's our goal so far. Any questions then? Okay, let's do a couple more problems of determining convergence or divergence, depending on how long these might get. For the next problem, let's look at this sequence. A sub n is defined to be n cubed divided by n cubed plus 1. So theorem 3 is really going to take over for almost all these problems. It tells us any approach we would have taken in calculus 1 in doing these types of limits is still going to work for the limits involving these things. So I want to take the limit as n goes off to infinity of n cubed divided by n cubed plus 1. Anyone see what that limit should be, just by inspection? It'd be 1, exactly. So if you told me this equals 1, that's perfectly acceptable. In fact, that is really, really encouraged, because once we get to, say, 11.6, 11.7, working this out step by step is really very tedious, and problems are already very large. Let's actually work it out step by step this time, and mention you ought to take that shortcut. So this is what the book likes to do for a solution to this thing. The limit as n goes to infinity is really just the horizontal asymptote of this as a rational function for imagining variable x. That horizontal asymptote would involve the coefficient 1 divided by 1, but we're taking a different approach. We look to the denominator, take the highest degree term, and divide everything by that term. So I'll go to the numerator, divide n cubed by n cubed, we will get a 1. Go to the denominator, divide n cubed by n cubed, we get a 1 as well. Plus, we take 1 divided by n cubed down below. So that would be the setup if we take the step-by-step approach. Then we have limit laws that work in the case we have a continuous function that says the limit of a ratio would be the limit of the numerator divided by the limit of the denominator, provided those both limits exist and the denominator does not tend towards 0. That would be very bad. But the limit of a constant is the constant. Then down below, we have a sum rule for limits. We take the limit of this constant, still the constant, plus the limit of this thing. So the whole work has been reduced to what is the limit as n tends towards infinity of 1 over n cubed. What would you say something divided by something that grows larger and larger with that value would tend towards? It ought to be 0, right? And it's really no different if this was variable x here and here in ordinary chapter 2 of the book. So this goes to 0, which is equal to 1. Then we're done. But this was the shortcut. In this particular case, we have a power 3 here with a power 3 here, which is a tie. If the power was 4, the whole thing would tend towards positive infinity. And if this power was 2, the entire value would be 0 in the limit. But with a match of even powers, we just take the coefficients 1 over 1. It's exactly this here. And you can always skip exactly from here to here. This is an encouraged shortcut. So if you look at the homework assignment, there is a lot of different limits here, but some of them are actually very, very fast. You're just potentially able to, by inspection, state the value. So as per the instructions, we can say a sub n, which is this stuff, converges to 1. And the meaning is, as n gets larger and larger, this entire quantity is going to become closer and closer to 1 itself. But any questions about that problem so far? How about one more for the road? Does that sound all right to folks? Okay, so one last problem. We'll delete the most important theorem in the entire section while we're at it, just for the need of space. And we'll take the look at this one, which is a sub n equals e to the power of 1 over n. So we want to take the limit of that. The trick to this one is we can take the limit as n goes to infinity of e to the power of 1 over n by making the following observation. F of x equals e to the power of 1 over x is continuous when x is bigger than 0. So on the domain from 0 to infinity, excluding 0, we have a continuous function. And there are very, very big implications for continuous functions and limits. One implication is if base e is a continuous function, then we can write this as e to the power of the limit as n goes to infinity of 1 over n. So the limit would commute inside the continuous function. The limit as n goes to infinity of 1 over n is no different than that value there, 1 over n cubed. So this would turn into e to the power of 0, which would be 1. So continuity can also be leveraged to solve many of these problems. We can then say on this problem, then a sub n converges to 1. Now we'll look at other interesting problems along these lines. Any questions so far about the sequences? Okay, that's all I have for folks then. One thing I should mention is Chapter 11 is a really gnarly chapter in this course. Not because it's necessarily horrible. If you look at section 11.1 in isolation, it's not too bad. It gets really bad once you're really deep into it, 11.8, when there's many, many different theorems, differences between sequences and series at the same time. So one thing that'd be really helpful, I would say, is a bit of pre-reading before you get to course, just to skim the main ideas that we'd be looking at for the day. That really helps with traction on the brain when you see the problems worked out in class as well. But if you have questions, feel free to stick around.